I'm Tim Messegee, and today we're going to be talking about how AI is shaping the memory market. And to do that, I'm joined by my three memory Rambus Memory All-Stars, Steve Wu, who is a Rambus Fellow and Distinguished Inventor from Rambus Labs, John Eble, who is Vice President of Product Marketing for Memory Interface Chips, and Nidish Kamath, who is Director of Product Management for Memory Controller IP. So, gentlemen, welcome. We got lots to talk about, lots of issues when it comes to AI and the impact on memory. So, why don't we start high level context setting? Steve, why don't you kick us off with what are some of the big developments in AI that are really putting pressure on power and performance requirements for memory?
Yeah, I mean, what we're seeing today is there has been tremendous advances over the last few years in AI, the kinds of models and the types of services that we're able to deliver. But, there's a desire to do more. There's a desire for higher accuracy, more functionality, and kind of richer results as well. And this drive from agentic AI now to just artificial general intelligence, we're continuing on that march. And in order to get there, everywhere around the ecosystem, we need more performance. And so processors need to get faster. Memory systems need to have more bandwidth and more capacity, and interconnects also need to have more bandwidth as well. What's really interesting about it all in terms of how it impacts memory is that, I mentioned that we'd like to get more capacity and more bandwidth in our memory hierarchy. And that's in part because we're manipulating more data. But
Yeah.
what's interesting about it right now is that the cache hierarchy, and SRAM in particular, is not scaling very well. And so at a time where we would like to get a lot more SRAM, and the fact that we can't really get it to scale in the same ways that we have in the past, it just puts pressure on the next layer of the memory hierarchy, which is DRAM. And so part of the things that we're seeing is not only are the newer models requiring more performance and more capacity, but you get additional pressure because the level above you, SRAM, can't really scale as well as it used to in the past. Those are just a couple of things that are really driving some of the changes that we're seeing in memory.
Steve, what about implications like, model sizes getting bigger or context windows getting bigger or changing the architecture such that, instead of kind of this one shot, uh, we're going to reasoning architectures and models?
Yeah, all of those things are contributing to a need for more bandwidth and more capacity. Like you mentioned, the longer context windows, so being able to
Yes.
have a conversation that is where the context is maintained over a longer period of time. That's important. And then being able to have bigger models that are more functional is important as well. And then even being able to share that hardware across many users means now we have to have more capacity and more bandwidth to support multiple simultaneous, say, inference sessions that are going on. So yeah, again, all those things are putting pressure on the memory systems in order to provide a better experience for the end users.
So why don't we start to drill down into, given that AI is kind of the Veruca Salt of applications, and that it just wants more of everything. Um, John, what are some of the kind of the technologies that you're excited about that can help us address the more bandwidth, more capacity kind of requirements that we have with AI?
Sure, sure. Yeah, Steve summed it up well that you know, these AI servers, the money going into AI servers is really tremendous, right? And it's buying more hardware to really do all the things that Steve talked about. But when you look in a server, most servers have two CPU sockets,
Right.
and there's only a limited number of memory channels that you can connect to that processor, either because of packaging technology limitations or just the size of the server type limitations. So one technology I'm excited about is something called MRDIMM, or multiplexed rank DIMM. A traditional DIMM or RDIMM, the speed of that memory channel is directly correlated to the speed of the DRAM on that DIMM.
Right. Right.
Right. The exciting thing about MRDIMM is that it adds memory buffers to that DIMM that kind of breaks that one-to-one dependence. We have logic chips that go onto the module that can multiplex and demultiplex pseudo channels, so that you can take two DRAMs in parallel and mux that data bandwidth into one stream back to the CPU. So, out of that one memory channel, you can effectively get up to twice the memory bandwidth. And that's done through two key pieces of technology. One is the multiplexed ranked RCD or clock driver. So what it does is it takes a stream from the CPU of muxed pseudo channel commands and addresses, and then it demultiplexes that out to two parallel ranks of DRAM. We also have the multiplex data buffer.
Okay.
So it interfaces to two DRAMs in parallel, but one single channel back to the CPU. It's bidirectional, so it's handling read operations coming from the DRAM, as well as write operations that are coming from the CPU. So I think this is really exciting. It's a way to go beyond the DRAM technology to get more bandwidth. In the market today are modules that run up to 8.8 gigatransfers per second, but the next generation will run up to 12.8
Okay.
transfers per second.
Okay. Nidish, what else we got from a bandwidth capacity
Yeah.
capabilities?
Yeah. So I will actually touch on something related to performance, but has been an afterthought in previous usages of memory controllers. So one would be the level of accessibility for system tuning. We have this feature, the telemetry, enhanced telemetry IP that we make available along with our controller that provides this level of visibility into the various sub-blocks of the controller. Now, it's important to note here that at least for AI workloads, there's a wide variety of applications. And the demand is so overwhelming that today's latest technology becomes obsolete tomorrow. So this means that we need a continuous improvement in processing and also the memory access efficacy. So telemetry enables both of these. And a related feature that has also been overlooked in previous memory installations is reliability. So in the data center world, that's known as RAS, like reliability, availability, and serviceability. And these features provide a way to make the system more robust and prevent downtime. So in the case of AI training, there has been studies that show that up to 20% of the systems are typically down either because of an error rate or some undebuggable error. Okay. And so this means that there has to be either a 20% over allocation of the infrastructure, or the systems themselves have to be made more reliable. So handling these memory on-die errors as well as link errors effectively is something that we also very importantly look at now with the various ECC and CRC algorithm support in the controller. So
Very good.
hope that rounds it up, Tim.
Yeah, thank you, Nidish. The other thing I was thinking about is we're starting to see some multi-PAM kind of solutions, specifically with GDDR. So can you explain, what is multi-PAM and what are the benefits there?
Sure. Yeah, I can touch on that. So GDDR7 has moved away from being only a graphics specific technology to something that customers are looking at for inference or in edge or endpoints, like depending on the power and the performance characteristics. And PAM3 is an interesting innovation for the physical links of GDDR7. It continues JEDEC's evolution of GDDR over all the previous generations in terms of improving the bandwidth. And JEDEC specifically wanted to limit the pin count and try to push the envelope on that. So what PAM3 does essentially is it uses 3 levels of signaling as opposed to 2 that was traditionally used in NRZ, or non-return to zero kind of signaling. And in conjunction with a 2-bit side channel that is part of the data path and can be used for error handling, PAM3 represents this reasonable trade-off that JEDEC was able to make between the number of bits transferred, the signaling voltage levels, and the bit error rates. So yeah, that's the latest hot thing in GDDR7.
Great. Speaking of hot things and power, you know, we were at the AI Infra Summit last month, and you know, had companies just across the ecosystem, from the, you know, folks who manage data centers, hyperscalers, chip makers, system makers, you know, everybody. Power was absolutely one of the hot topics, and pun intended there. The you know, they talked about a roadmap for racks going to in 2027, 2028 timeframe, 1100 kilowatts. That's a megawatt. That's megawatt racks, and data center campuses at gigawatts. At gigawatts is how much power you power a city with. I mean, these are extremely high powers. You know, in that context, I mean, it's going to take a village, but I mean, in that context, what can we do, you know, with the kind of solutions we do to help manage the power? And John, I thought, can I ask you to talk about how PMICs, what's their role in kind of this managing the tremendous power that we got to manage here?
Yeah, across our entire product portfolio, we are looking at ways to increase power efficiency. And that's just a major requirement to be a part of these solutions of the future. Now, you mentioned the PMIC specifically, and I think it does play an especially important role in the data center and in the memory subsystem. You know, the first role it plays is that it helps the overall system power efficiency, because what it allows you to do is deliver a higher voltage, lower current power supply to the DIMM directly. So it's up at 12 volts, a moderate amount of current. And then right there on the DIMM, it can then generate all the precise voltages that are needed at higher currents. So that's just, you know, good policy to start with.
Right.
Now the PMIC is super, super important in a gigawatt data center or a megawatt rack. Because if you think about what the PMIC is doing, is it's taking power in and it's delivering power. And it needs to be highly efficient. And every 1/10% is a huge amount of power loss. You know, so we are trying to eke out every, you know, 1/1000% that we can in that efficiency. The other thing a PMIC allows you to do is it's a very tunable and controllable device, so that on a per module basis, you can actually tune the voltages to get that right power performance trade-off
Okay.
on a particular application for a particular DIMM. The other thing the PMIC allows you to do is it does provide telemetry, you know, back to the data center operator. So at a very fine-grained resolution, that operator can manage its fleet by, you know, detecting what are the currents, what are the voltages, and what's the temperature of the PMIC. There's a number of different things there. So I think that is a key component on the DIMM and the memory subsystem to help to be one of the solutions
Right.
for this challenge.
Steve, what about from an architectural standpoint? Are we going to see maybe different computing architectures to help address power?
Yeah, I think John really gave a great description of sort of why these components are important and kind of how power delivery is changing in the data center. A lot of it comes down to understanding, well, why is the power being spent in the first place?
Right.
And in a lot of cases, what we're seeing over the generations is that a larger fraction of power is being spent moving data back and forth between chips, especially in the case of memory. We see a lot more power now being spent moving data from DRAMs, for example, to the processors that are using that data, and also between processors. So a lot of times in these large AI jobs, you split them among many engines at the same time. It's not unusual for the largest kinds of models to be employing more than 10,000 engines on the same problem, at one time. So if you really think about like what are the ways to minimize, say, data movement and help reduce the amount of power that's being pulled in the system, it's really to pack the components in more tightly, and that will reduce the distances that the data has to move. Now, the downside of doing that means you do have to get more power into these racks and into these servers, and that kind of speaks to the problem that John mentioned, which is
Yeah.
if you don't want to melt the wires, you have to go to higher voltages and to deliver, the amount of power that you really need. The other kind of consequence is, well, these high voltages that are coming now into the racks, they do have to get stepped down to what the components need. And as John mentioned, that's where the PMICs become important. And so there's an opportunity now for more silicon kind of in these servers to help step down this power. Now, the last part of it is really, once you've got that all together, then you have to figure out how to cool it. And so there are physical design challenges with trying to provide the right kind of cooling. We're seeing liquid being adopted more, especially in AI. And so now the design of the systems have to physically manage, the ability to have liquid coming in and to use, say, direct contact cold plates or something like that to wick away the heat. So we are seeing these kind of architectures where we're trying to densify the systems and minimize data movement. So you see people having multi-reticle size, GPUs and things like that to minimize data movement. And then we're seeing some of the physical aspects as well manifest themselves in how the racks are built.
Boy, liquid cooling was an interesting topic again at AI Infra Summit, in as much as for okay, big greenfield deployment, you're building it, you understand what the plumbing requirements are going to be. We're going to put in liquid cooling. There is an enormous installed base of data centers that are really not prepared for liquid cooling. So it just was one of the other kind of challenges we have to get over. And kind of it's a big inflection point also, because if you go back a couple of years, it was always, all right, not always. The whole story is only a couple of years old, but the story was definitely training, training, training. Now, 2025, there's been an inflection point. Folks were talking about inference, and inference because of, some of the latency requirements, some of the real-time performance requirements it was not all going to be performed in the heart of the big data centers. It was going to be, we're talking about it's going to have to be done at the edge or even in endpoint devices. Nidish, talk about this greater shift towards inference and generative AI at the edge and in endpoint devices. What are the implications of that for memory?
Thanks, Tim. We are seeing a lot of the workloads actually now starting to move the focus to inference as well. And there are two key points here. One is this overall size of the system, and you are really looking for a high performance in a small package. And GDDR7 fits the bill very well. We had a comparative study of LPDDR, GDDR, and HBM, which one is able to meet the edge or endpoint requirements. And we are able to achieve a certain performance point for edge applications with fewer number of packages. And that is critical for something that needs to be certified to work in a wide range of temperatures and power budgets. And the other thing that's afforded to inferencing applications by GDDR7 is the robustness of the link itself. So GDDR7 protocol has built into it a retry mechanism. So if there are transient errors arising on the link, or either because of the link state or because of something gone wrong on the memory die itself, GDDR7 protocol allows those transactions to be replayed, and that way the microprocessor or the overall system processor does not have to intervene, waste cycles, and commensurately some amount of power resolving those issues. So those are two innovations where GDDR7 really can help with inferencing. And then downstream, we are also seeing some of these similar aspects being discussed for LPDDR6 as well.
Excellent. Well, we'll come back to LP. But John, I wanted to ask, what's happening on the for clients and this trend of more inferencing now pushing to clients. What's the impact on client memory?
Yeah, good question. Nidish was just talking about having these extra auxiliary processors, say, in your laptop or your desktop at the endpoint that can do this inferencing locally using GDDR7. The nice thing is whenever you have extra compute with extra high bandwidth memory, the CPU needs to be capable, and also it needs its main memory.
Right? Keep it
Not
balanced.
only to keep this is a balanced system where it's doing its general purpose work, but it's also helping orchestrate that inferencing. So this term of the AI PC has become very popular. What that's driving is more memory bandwidth and capacity needs for that central SoC or CPU. So there's some exciting developments in client memory. Typically, desktops use UDIMMs or unbuffered DIMMs. Laptops will tend to use either die down or small outline DIMMs or SODIMMs. JEDEC has introduced the concept of a clocked UDIMM and a clocked SODIMM that introduces a clock driver chip on the module, which reduces the jitter or cleans up the jitter that's coming from the CPU. And what that does is it allows the module and the whole memory, subsystem to run at a higher clock frequency, and it can close the system timing budgets much more effectively. So that's very exciting. And as you move into these, higher speed clocked UDIMMs and clocked SODIMMs, there's not just this clock driver. You also have a new PMIC, which can provide the extra power that's needed for that module running at that higher speed and capacity. And as always on these modules, there's a SPD hub, which is a non-volatile memory, but also provides the sideband interface and a place for telemetry of the temperature of the module, which gamers like and other folks.
Yeah, absolutely. Absolutely. Steve, other thoughts about inference implications on memory?
Yeah, I think, as we've watched workloads in the industry shift more from training to inference, like you mentioned, probably the most titanic shift we've seen are with, engines like ChatGPT, where, a lot of cycles are going into training, but man, these days, there's so many cycles going into inference.
Yes,
It's
absolutely.
it's natural, right, to think about the
Right.
workload being different and to think about either new silicon. And so, for example, NVIDIA announced Rubin CPX, which is also going to use GDDR. It's natural to kind of think about, for that type of workload, how do I really tailor and use the right kind of memory and the right kind of really processors in my system tailored more towards inference. Like Nidish mentioned, there's other kinds of memory now that we're starting to see, and I think as you mentioned as well, there's a wide range of systems that we're going to want to do inference on. Some of those are willing to accept maybe memories that are less mainstream from the past. So some systems will for example, be using more GDDR7, I suspect, and more kind of graphics cards because they happen to be available in the systems. For things like phones, it's going to probably rely much more on specialized processing cores that take advantage of, higher performance, processor transistors as opposed to being able to put, many other types of memory, for example, in the phone. So I think there's going to be a big change up and down the stack for various kinds of devices. And, I think what happens in those systems is going to depend a lot on the type of system that you're dealing with.
And Nidish brought up LP. Why don't we talk about that a little bit? Because it's certainly coming up in the conversation for AI more. And obviously, it was designed for mobile phones, and so it's got some characteristics like you've got to keep traditionally keep the memory very close to the processor. Um, uh, and what are some of the implications of trying to either take advantage of LPDDR or the characteristics of LPDDR more broadly, like in the data center or in other client devices? Nidish, you want to start us off?
Yeah, so for LPDDR, there are two things going for it, and that brings it as a contender for what would have been for an application for server DRAM as well as for GDDR. And one is the trend going from LPDDR5 to LPDDR6. The bit rates have gone up. At least 50% over the LPDDR5X generation. And that means currently LPDDR6 as spec is faster than the DDR5 in the speed bins. And secondly, the LPDDR memories have also benefited a lot from mobile platforms where they want to package and pack as much memory capacity into a single stack, right? And that combined with this faster interface means now you are starting to reach the right capacity and performance point. So interchangeably, LPDDR6 and LPDDR5X and GDDR7 will be used as candidates for inference directed systems. That's the main thing going for LPDDR6. And on top of it, there's, of course, the legacy power support, LPDDR5 and 6. They have ways to lower the clocking power and also the toggle rate on the data pins with data bus inversion and such schemes built into the protocol. So it can address some of the performance and hit the power requirements as well.
John, what about in clients?
Yeah, LPDDR really has made a strong transition from mobile phones into other, client devices like laptops and even some desktops. Up until now, LPDDR has always been used die down on the motherboard, as you
Right.
mentioned. It needs to be very close to the CPU or even co-packaged with the CPU. This probably so far has limited its adoptions in certain areas where that particular segment wants a module where you can replace it, you can upgrade it. And I think also having memory disaggregated is often a good business strategy because it allows you a lot more efficiency and flexibility in your supply chain management. But a recent new memory module form factor called LPCAMM2 has been introduced along with its connector technology. And it allows it to be very close to the CPU with high signal integrity. And this has really enabled LPDDR memory to start being used in places where you want a module form factor. So I think that's very attractive. It requires a special PMIC because the voltage rails of LPDDR are slightly different. So that's a product we're excited about. And yeah, so I think that has a bright future in client. really bringing the benefits of LPDDR memory while keeping the benefits of a module-based implementation.
Exactly. Exactly. Steve, what about it's not really an enterprise grade data center product. Nidish was talking about RAS and reliability. Are there things that you can either incorporate LP into your more mainstream roadmap or make LP kind of more robust for the data center?
Well, yeah, I mean that's really the $64,000 question here is if you take a look at LPDDR, LP memories in general, I mean they're fantastic at providing bandwidth per watt, and that's important in a lot of different areas, but especially in AI where we talked about the importance of power. So being efficient is very important. One of the challenges with it is in the past LP in the types of systems it was designed for haven't really had the same kind of RAS requirements
Mm,
as servers. So the ability to do things like chip kill or the ability to tolerate a large number of errors and still correct for them and have the system still function. Those were not as important of requirements in the mobile space as they were in servers. So there is a lot of there's always this desire to try and figure out how can we take some of the really, really great things that come out of mobile memories, like that bandwidth per watt. How can we make them more applicable to, say, main memory? And like John mentioned, LPCAMM2, it starts to make it more consumable as a type of memory for processors. The challenge is how do you improve the reliability? And so the trade-off that's going on now is, how do you think about providing a higher level of reliability in those kinds of systems? And are there things you're willing to trade? So I'd say right now that's a really active area of discussion within our industry. And there's a lot of very interesting proposals that are looking at exactly what you mentioned. How do we bring the benefits of that performance per watt from the mobile memories, into the next generation of main memories? And is there some kind of hybrid that we can develop that brings the best of both worlds?
great. Well, why don't we wrap it up with a little bit of future casting? As we go to from generative to agentic and ultimately to autonomy, what are some of the opportunities for memory as we go forward? John, let me direct that to you, and then we'll go around the horn.
All right. That's a tough question. It's very broad, but but yeah, I think in my mind, right, AI today is it's great at answering questions, making my emails sound better. It can generate rich media content that
Exactly.
serves a purpose or gives someone a chuckle. But I think as it moves, I mean, I think AI is going to start controlling physical things in our lives via robotics and autonomous vehicles.
Absolutely.
That's exciting but scary. Um, and so in my mind, like the overall reliability, the resiliency, the security
Yes.
memory subsystem, while it's inferencing and running this model and doing things, I think that's very important. The overall quality of the semiconductors and the architecture and the system. So, I think today a lot of times when we're developing products, there's always that performance vector, there's always that power vector. But I think this, quality and reliability and resiliency and security vector is going to become very important. So I think that's an opportunity to really differentiate and make this a reality and make it safe.
Yes, exactly. Absolutely. Nidish, you want to add?
Sure, yeah. So there's two things I would double click on what John said. So when we saw the bigger cloud movement from regular servers to very specialized systems to serve different kinds of workloads within the cloud infrastructure. We saw that there was an emphasis on how do you protect one tenant's data from another tenant. And we will see that requirement come in with AI models, with AI inferencing data. There's also privacy concerns in various geographies as well. And inline memory encryption to provide this real-time encryption of data that's stored actually in the memory die would become important. So right now that is being cast aside because everyone's chasing the performance vector. But we will see that drive towards encryption. And along with that, we would also see some form of processing in memory, because that allows the homomorphic encryption algorithms to be run without a full encryption engine. So we'll see those come online in the future.
Yeah, excellent points. Always, we start out in the Wild West, but we get to civilization eventually and make sure everybody's property and data are protected. Steve, you want to take us home?
Sure. Yeah. I think just in addition to the things that both Nidish and John have mentioned, what I'd say is, as an industry, our job is to continue to do the kinds of things that we've always done, which is to provide better, more cost-effective hardware. In the case of memory, it means higher bandwidths and capacities, and really even for processors, it's higher performance. We've seen time and time again that when we provide better, more cost-effective hardware, compute becomes cheaper. And what that does is it drives better adoption and higher productivity. And it forms a bit of a virtuous cycle. And once you do that and you're able to show better models or more accurate models or things that are more feature rich and productivity increases, then the demand goes up. And that increased demand spurs another cycle of better, more cost-effective hardware. And so the challenge, for our industry is to continue kind of pushing that virtuous cycle forward by providing, better hardware that's more cost-effective, so that the folks that are doing things like, developing new models and writing software around the hardware can continue to deliver, better user experiences that keep that whole cycle going.
Excellent. Thank you, Steve, John, Nidish. Thank you, gentlemen, for your insights. Thank you, everybody, for joining us.